Last week, I traveled all the way to London for an event organized by the London Java Community Group, which was held at the Couchbase offices located on King William Street. This event was organized by RecWorks, the London Java Community Group, and Couchbase. To this event, I had sent my application form at around June, July, and right about the same time, I got my first reaction. And from that moment onwards, we kept on having discussions on when would this event be organized, and of course where. We ended up setting up a fixed date on the 10th of September, and for this meetup there were two speakers invited. One of them was me, and the other one was Amin Talukder. And Amin did an excellent work in explaining how to use tools for the JVM and how to research and see the garbage collection working in real time. My two contact points for this meetup were Marcin Kruglik and Nick Fehrenbach. And for now, I want to say a massive thank you to the London Java community, to Marcin and to Nick for organizing this event and making it possible for us to find a good date that would suit my availability and the availability of Amin. Also important to note that me traveling to the UK meant that I needed some extra documentation. So that means that I had to refresh my passport and to renew it, and I also had to ask for special documentation to be able to, if asked, show why I was then traveling to the UK. It is important because this is how it works when you travel internationally. It is only very unfortunate that only the last time that I visited the UK, I didn't have to worry about any of this except for carrying with me my national ID card. Nowadays, because of Brexit, I have to worry about getting my passport renewed and getting all of this documentation just to justify the reason of my visit to the UK. And for that, the London Java community, Marcin and Nick, were very helpful, and I thank them for that because they were able to give me on time the documentation that I deemed necessary only after reading the website of the government of the UK. I wasn't able to get anyone over the phone to get some more clarifications. But these were the only hurdles that I had to face. For the rest, the trip was great, the stay was amazing, and the meeting was even greater. I had a great audience, a very energetic audience asking questions all the time. We had great debates during and after the meetup. It was great to see everyone. Thank you everyone for coming. And what this video now is about that presentation. So I'm going to do that presentation over again with extra hands-on demos where we are going to see the performance of the application against a fully reactive versions of the applications that I've shown in this presentation. So if you have been in the original presentation at Couchbase in London, it is of your interest still to see this video until the end, because I'm going also to show how these applications react when they are connected to a database. Therefore, only allowing for us to test processes that are heavily dependent on input-output operations. For the rest, the presentation will be the same. And therefore, if you haven't been to the presentation in London, this will also be important for you if you are interested in these topics, because the discussions will still be around the same topics that I discussed there, and the full presentation that I gave in London, I will also try to reproduce here. So there will be the topic of the discussion plus the extra tests that we are going to do throughout this video. I hope you enjoyed the video. Are you ready for that? Because if you are, I'm ready too, so let's get into it. So let's get started. My presentation is Could Java Virtual Threads Cast Away the Usage of Kotlin Coroutines, and what experience can tell us? How coroutines have changed the JVM programming world and how Java Virtual Threads can change that. This presentation was made possible by Couchbase, RecWorks, and the London Java community. Thank you to all three of them, the people who organized them, and for everyone that came to the event. But first, let's talk for a few minutes about me. So who am I? I'm João. I've worked for more than 10 years in software development. I've studied telecom engineering at ISEL Lisbon, and I've worked in different companies in Portugal, Spain, and in the Netherlands. I'm a certified Kong champion, I'm a certified Java developer, an OCP 11, and I am a certified Spring Professional 2021. Outside of the software development universe, I also love to grow plants. This is my yucca, which is much bigger at this point. I also like to try with different kind of plants. In this case, these are gooseberry bushes, and that's actually an elderberry bush growing on a vase at this point. I also like to make stuff out of old materials, sometimes out of old furniture. I make new furniture. This behind me is something that I made out of an old IKEA bed, for example. And of course, this is me, and this is me at the beginning of last year when I was starting to create my channel Jaspertech, which is available on YouTube, and you can watch the videos there if you want to know more about software. I'm always putting there new videos all the time about new topics about software development. Although many times it seems like all I post is Kotlin, but I have done things about Haskell. I have done videos with Java and with Bash scripts. So have a look at it and see if you enjoy any of those videos. But let's first talk about threads before we delve into the topics of the presentation. This is important so that we can know exactly where are we at this point in history, at this point in time. So in 1995, Java 1.0 came out, and with it, green threads came along. These were very simple threads, and the idea was that they would perform better than other threads. The thing is, they would only work with CPUs with only one core, and that led to some other issues. And in 1998, because of that, Java 1.2 came with the transition to native threads, what we now call OS threads, operating system threads, or simply saying platform threads or system threads. In 2004, Java 5 came out, and with it, the concurrency utilities, thus everything that allows us to use the executors and launch threads via executors and establish different thread pools. In 2011, the Kotlin language was announced, and Project Loom was announced a few years later in 2014. And in 2017, Kotlin 1.1 came along with the introduction of Kotlin Coroutines. And there we would be able to use the first implementation where we would be able to execute sets of instructions that would be based on the principle of continuations. With, in general terms, in a nutshell, continuations means that instead of having to copy the whole context of a thread when performing a context switch, we would only copy the context necessary to perform certain operations for certain sets of instructions. This would mean that we would be able to release the resource associated to our running execution, which in this case are threads. And that is what coroutines did in a non-preemptive way or a cooperative way in this case, so they would release the control of the thread voluntarily. In 2019, Project Loom was available to test in early access builds, and in this case, when it was available, it was already established that Project Loom would have virtual threads and not fibers, which were a sort of coroutine, but they were not considered lightweight threads. They were lightweight just as much as coroutines are lightweight, but Java virtual threads were the first implementation for the Java virtual machine of lightweight threads that would be able to be distributed across different threads in different cores. In 2022, Java 19 and the preview of virtual threads. So this was a release that would contain Project Loom, and it was still available just for testing, and it was a preview that where we would be able, and it was just another release that it was pivotal for us to test something that was getting closer to a version for production. And then finally in 2023, last year, at the end of last year, Java 21 came out, and the official release of Java Virtual Threads came with it. So what this should tell us is that from 1995 up until this year, 2024, we have seen a huge evolution between what we are trying to do with the Java Virtual Machine, and that is to take the best profit out of it, to get the most performance out of it. And here we come to the first example that I have to show. This is an example that is an exercise about how to choose between virtual threads and coroutines purely from a code basis. So that means that considering this case, what should we use? And so the case is, in where I work, and not just for the current project, but for other projects, there was always this annoying situation at work where you would have to get different data from different cloud environments or different databases or anywhere where the data was related in a conceptual way, but physically the data was not related. So it's sort of like an ER model in different databases, if you will. And the idea was to be able to extract this data and make it into a ER model into another database and be able to use it correctly. This is what we have here, a parallel to that example that I have at work. Of course, because I cannot talk directly about examples at work, everything that we see in this presentation is a list of different examples created in a parallel way to real life examples. So they are changed, the concepts are changed, the domains are changed, but the principal idea behind them is the same. So in this case, I'm fetching data from where? From 3 different cloud environments, where in one environment I have a database and I have a Spring service using essentially using a database that contains users, another cloud environment that contains the comments that the user has made, and another one with the posts that the user has made. These are all connected together via a user ID, and there is an internal service that will collect all of this data together and put that data into another base, into another cloud environment. But that data will be put there in a relational way. The problem with this is that not only this is a horrible model, so what I say here at the bottom of the slide is very important. So this fetch is a fetch all datagram, which is a data diagram, which is a horrendous old way to fetch data for server side, but great for mobile, maybe sometimes, because mobile also has this kind of many times with mobile you have to get different data in separate requests. So that's why I'm mentioning here mobile, maybe. But one way to implement this is by using Java Virtual Threads, which is kind of the first thing that we look at when we look at the new version of the JDK. So if we have Java Virtual Threads on the JDK 21, why not jump into the bandwagon and just start with Java Virtual Threads? Well, here's the thing that we also need to consider when we start working with virtual threads for this particular example. We have to consider that we are running three different tasks, and we want these three different tasks to run in parallel because we already know the user ID. We want to fetch the data for one particular user, and we have that user ID already. And so we are able to fetch all the user data right over here. We are also able to fetch all the user posts from over here and fetch all the user comments from over here. Now, the way that this code is built is by using a try with resources that creates a scope for a structured task scope, and it will shut down all failure. This is another way to describe something that is used in these kind of implementations, this kind of optimization for the use of threads, which is structured concurrency. And this is an example of using structured concurrency with Java Virtual Threads. If we look at the example, we see that the scope will join, and then it will throw if it's failed. So when we are launching this stuff, so then these tasks are made like this with a fork from the scope. So in here we have already 3 tasks running as a fork, and as you can see, the way to do this in Java is quite verbose. And we also see that, for example, we are joining here, so that means that the whole scope will wait here until all the tasks are finished. If there is no exception, then the code will continue. If there is one exception thrown by any of the forked tasks, then that means that in here the scope will fail and the code will fail here. For every single of the deferred elements that we get from the scope, we then need to call get to get the actual value that has been returned from the task, which is the value that we get from over here with this fetch user. Finally, if that is the goal that we want to achieve, we can update the UI or update the database right over here. And then we can just log that the process is complete. But here's one thing that is quite annoying about this code. It is highly verbose, and to declare everything takes a lot of code typing. One of the things is that we need to declare the scope this way. It will shut down on failure, so if there is an exception, then it will activate structured concurrency, and that means that everything will stop and will throw an exception here if anything has failed in any of the tasks. But then we also need to declare every single one of these tasks this way by the use of a fork and the declaration of an instance of a lambda over here. And we could use an alternative to this, and that is we may be able to, for example, use a start virtual thread here, for example, at the beginning of the block of this code. But as you can see, the code will get much more complicated than what it already is. That means that we would have to wrap all of this function into a thread start virtual thread, which is not ideal in this case. But we can have a look at an example now in our own code and see what do I mean with all of this. So if we go over to our code, we can see that we find here the load user data method, as we have seen in our slide, that contains this try with resources, and it uses a structured task scope which shut down on failure. This only means that our structured task scope will fail once one of these forks fail. So here we can find the code for the load user data, which is the method that calls the implementation that we've just seen in our slide. Here we can find the structured task scope, which is inside a try with resources that will allow us to use the scope in a way that we can fork multiple tasks for it. One is the fetch user, one is the fetch user posts, and the other is the fetch user comments. All of these are deferred values that we can then wait for them with the scope join, and then after the join has complete, that means after we completed these forks, then the join will allow the run time to further go on to the next line, to the scope throw if failed, and if any of these forks have failed, then we will see that an exception will be thrown. And to get the results from the different forks, we need to get the value from the deferred values, which is this get call over here, and on all the other two, the post deferred and the comments deferred. Finally, we can update the user UI. If we run these tests right now, in this case the Java structured concurrency test, we will find that everything runs correctly because we are not expecting to find any exception, and we are actually not making any assertion. This is only for us to be able to run the test. Actually, the only assertion that we are making is that when we get all the users, so meaning that the result from the one call to the load user data, that we only get one user. That's essentially the purpose of this test. But let's cause something to fail. If we go here to load user data, to make this fail though, and because this is Java, we need to use a few tricks. In Kotlin this is easier, and you will see this later, but for now let's try and make this throw an exception in Java. So at this point, when we create with this scope, that means that the implementation of the lambda needs to return. That's one thing that in Java we need to do. And another thing that we need to do right now is to throw the exception. One way to do that is by just throwing a new runtime exception, for example. But Java doesn't allow us to compile this because it says that this code is unreachable. Well, the trick to do that in Java is simply to do this. Now Java doesn't really know what to do, and it doesn't find that code anyways. And if we run the test, we're going to see something interesting. With the Java stack trace, we are able to find out where exactly the exception has occurred, and actually it was over here. But this is not where the exception was initially thrown. Let's now debug the code and see where that exception has been thrown. If we go over here and we just run this in debug mode, we will find something interesting. First of all, here, this is where we wait for all of the tasks to have completed. Because this is run in parallel, we could say, okay, the exception has been thrown, but nothing has happened yet because I'm just holding this breakpoint in. If I do one step further, nothing has happened yet. But however, everything has already been executed with the forks because I just made one step further, and that means that the user deferred, the post deferred, and comments deferred already have a value in them that we need to use, that we need to be able to access with this get method. But if we do here a throw if failed, this is where everything fails because, again, an exception has occurred right over here. And this is where the principle of structured concurrency happens. That means that everything has been cancelled at the same time. At the moment, one single fail has occurred, which is interesting for us because this is an all or nothing kind of thing. We want to get all of the matching values for the user and not just the posts or the comments. We want all of it at once. But as you can see, this is quite a verbose thing to do. And we mostly don't want to do this kind of things in code, even if it is Java. So another alternative to solve this problem would be maybe to convert this code into its matching Kotlin version, because we can use Kotlin and Java in the same code, so perhaps there was a possibility to improve the code. The other solution, of course, was to convert that code into Kotlin, as I just mentioned. So this is the conversion of the code that we've seen before from Java to Kotlin. And what we see here is a shutdown on failure instance right at the beginning that we then use with this use keyword that essentially means the same as try with resources. This shutdown on failure is the same as what we've seen here before with the structure task scope dot shutdown on failure. It essentially creates a new scope that allows us then to create the different forks needed to perform what we want to achieve, which is collect all the different data and put it in the processed data object type. When we use this, we can then call these fetch user posts, fetch user comments in the same way as we did before. And then what we have to do is exactly the same. We join and we do a throw if failed. And then to get the different values that we receive from the calls of these methods, we can just call the get, just as we did before with the Java version. The difference here is that it is slightly less verbose and it's easier to read. But this is not a major advantage at this point, and maybe it doesn't justify making a conversion to Kotlin. And if you're already using Kotlin, maybe this would already be a good solution. However, we can see that it's still highly verbose. We are still using a shutdown on failure. We use the use keyword, which saves us some code when using try with resources. In this case, we are not catching any exception because this is what the use does for us, but we still have to fork the different tasks. And again, we are faced with the same issue, and that is that at this point in this process data, we need to make these 3 different calls just to get the result from the inside and then update the system with the process data. We are left with an alternative if we want to do this in an asynchronous way, which is to wrap the whole code with start virtual thread. But there is another thing that I didn't mention, which is also not very desired with this implementation, but also with the previous implementation. And it has to do with cancellation. But before I talk about cancellation, let's have a look at this in the code and see what we can find. So the code is this one, and we can first have a look at the implementation of this alternative, and that is this one over here. We can see our load user data, we can see a shutdown on failure, we can see the use over here, which again is the same thing as the try with resources in Java, and then we call all of these different forks on this single scope. We do a join and we do a throw if failed. Finally, we process the user data and then we pass as input arguments the get values from all the different deferred values that we get from the different scopes. And then finally, with the new process data object, we update our system. But let's first have a look at this in the same way that we did before and try to cancel this task. Now, I mentioned before that it should be easier to do this with Kotlin. Well, it is, for the simple reason that with Kotlin, we can just throw a runtime exception. And the reason why we can do this is because in Kotlin, there are no checked exceptions. It is not the only reason, but this already simplifies a lot. And another thing is that there is no mention here that fetch user comments at this point is dead code. So we can just run this code the way it is. And what we are going to see probably is the same thing. What do you think it will happen now if I run this code like this with a runtime exception? It should fail right over here, right? So let's see what happens when we do run the test that checks this service. That test is over here. That is the JVT Kotlin Structured Concurrency Test. And this one will just create a user service VT. So that's this one, not yet the user service from the production code. And then we just call here the load user data for user with ID 1000, and then much in the same way as I did before, we check all the users that have been collected together in the process data object. We can have a look at how this works. We have here a dummy system that uses an atomic reference with a mutable set inside of the process data objects, and there we will add the new data of the user. So each one of these calls, the fetch user post, are simulations of something that we could use in production, but of course the implementation is very simple. We've got different sleeps with the different calls, and they're all 1 second. So first let's run the successful test and see what happens over here. And make sure to pay good attention to all the different information that we are seeing on the screen at this point. So when we run this test, we can see already that the test failed. And now let's have a look at exactly what happened in the test. If we go here to user service, we can see already that in the stack trace of our exception, we can see that the code points to this single line over here. And of course it is so, because this is where the error happens. Well, actually the error happens here, but that gets registered in the scope. And then when we call this, then all of this will fail, and then we should get an exception. So if we take a look right over here, we see that the test only took 16 milliseconds. But wait a minute, we have 3 different tasks that are running in parallel, and they were sleeping. That means that if we go here to fetch user, we see that they were sleeping for 1 second. So how come the test only takes 16 milliseconds? Well, that is because by throwing this exception, we are interrupting the runtime of all the other scopes. And that means that we did not achieve something important when we are talking about structural concurrency, which is a graceful shutdown. So that means that we were able to interrupt immediately what we were doing, but we didn't let our other tasks to be aware that one of them have failed and perform whatever sets of instructions we want to perform to guarantee a graceful shutdown. Think of things like losing data, getting the right information, informing the system that certain requests have been made. Have these requests been successful or not? Maybe we want to store the successful results for another attempt. I mean, there are different things that we could do if the whole scope has partially failed, but some tasks have actually succeeded. But going back to the clear advantage of converting this to Kotlin is simply that in terms of syntax and semantics, we were able to save a lot of code. And that means that we have less boilerplate code, and that means that the code is easier to read. But it is still quite verbose at this point. It is still maybe not the best code to use, and maybe there are better alternatives. And also consider the cancellation, which is also something very important when we are talking about structural concurrency. So let's now have a look at the solution that we have then chosen to be the better option for our case. Let's see. This was the best option that we could find for our own code. As you can see, it looks much better, it looks much shorter, and this is pure Kotlin, and this is using now, instead of Java virtual threads, it is now using Kotlin Coroutines. What we see here is a launch, and in that launch we are running a set of instructions. That launch is happening via a context that is using the dispatcher's I/O. These are dispatchers that are specific for input-output operations, which is what we want if we want to access databases and if we want to make post, get requests. Essentially, if we want to make requests across the web, whatever requests they are, those are really things that will work much better with input-output dispatchers. So what we do here is essentially creating 3 deferred elements, just as we did before with Java virtual threads, but in this case we are using async, and we are launching 3 different coroutines in an asynchronous way, and these different coroutines will fetch the different data that we need. All that we do then is an await. We don't have to tell the coroutine scope to throw an exception if an exception occurs in any of the individual coroutines. And then finally, we can just call the process user data with the user posts and comments, and then we can just log that the process has completed. And another advantage to this is that we can launch this via a suspend function, which gives us certain advantages, which means that we can run them either in an asynchronous way or simply just run within a coroutine scope, which can have its benefits. We can then put this in a library and then reuse it as much as we want, and then have those choices available to us. So this is still a bit verbose, but it's a lot better, especially because we only need to call this async in this way, and then declaring a coroutine context and launching a scope this way is much less code than what we've seen before. And another thing is that this is not blocking. We can use this inside a suspend function, and then we can call this in a non-blocking way. And even if we want to call this in a blocking way, then we just call run blocking and wrap this around. It is really only our choice. But the code, it's quite arguably much more readable than the two options that we have seen before. But there is another advantage to this code, and I will show that now in our code implementation via our IDE. So if we go over here, we can see the selected option for our implementation right over here. We've got the same load user data, but now it's implemented with the suspend function, and now we are starting this from a coroutine context that has an input-output dispatcher and launches this scope right over here that has these sets of instructions where we then fetch a user defer, post defer, comments deferred via async calls to launch 3 different coroutines that then are responsible to fetch the data that we can then wait for with this await call right over here. And then finally, we can process the data, and then the process is complete. Now to test this, we can just run the test that it's located over here. This is the user service test, and it simply creates a user service, the one that we have here available for the production code, and then we can just load the user data, join to wait until it finishes, and then see how many users we have gotten. And again, in this case, we will get just 1 user. But let's have a look at how the load user data is actually implemented right now. If we go right over here, we can see that for every single call, we've got now a delay of 3 seconds. And I want to prove a point here. If we run this code right now, it will take only 3 seconds to run. A little bit more because of the overhead of the unit test itself, but let's first start out by running the test that way and see how long this will actually take. You see, 3 seconds. Why? Because we are sending 3 asynchronous coroutines. Now the process has completed in 3 seconds, but now let's simulate something that could fail right over here. But instead of throwing an exception, we are going to use the mechanism that is available for Kotlin Coroutines that is simply called cancel. This cancel function will signal the current coroutine to fail, and it will signal all the other coroutines also to fail. But here's the thing about this. Because Kotlin coroutines are non-preemptive, that means also they are cooperative. That means that signaling the coroutine to cancel, it only signals all the other coroutines of the same scope to also cancel, but it doesn't immediately cancels them. So comments deferred is the last call that we are making. It's the last synchronous call that we are making. And so that means that when I call cancel over here, the other ones are already running. So that means that the other ones are already suffering a delay of 3 seconds. So in Kotlin Coroutines, when a coroutine has been signaled to cancel, it will cancel immediately, or it will wait until the delay has completed to cancel immediately afterwards. So if I run the test again with this cancel, how long do you think that the test is going to take to run? Is it going to be 3 seconds or less than that? Will it be immediate as we have seen before with Java virtual threads? Let's see what happens. Now, it has failed, and it has failed also in 3 seconds. And if we look at the stack trace from our exception, we can see that the code actually continued, and it continued until the end, and no user has been added to that set that is being stored in our atomic reference. And this is fine. It only means that this has been cancelled and that somewhere an exception has occurred. If we look at our test, at the user service test, we can see that this runs through a run blocking. And this run blocking, the only thing that it does, it creates a coroutine scope where we can then make these calls, the load user data, because it is a suspend function, and then we do a join. But this doesn't take into account any exception that has occurred. So that means that over here in the logs, we won't be able to find anything else except that the collection doesn't have size 1 and now has size 0. We can do something else, which is we can throw a cancellation exception and see what happens. Which in this case is exactly the same, because that is part of what cancellation does in the background. But this is still taking 3 seconds. Should we say that we want to immediately terminate the execution of this function? Or should we let it shut down gracefully? That is an option that we need to think about when we are using this kind of code. Another thing that I want to show is that if I call a cancel over here at the first call for the user, we should be able to have a much faster cancellation. And that is only because when we do this, the first one cancels immediately. The other coroutines don't get to have that delay. And so they are immediately stopped because because the coroutines haven't reached the delay yet. So this was part of the dynamics surrounding the choice of the best solution for our case. In this case, virtual threads didn't really convince us, and that is purely because of design. Coroutines and Java virtual threads follow almost the same principle. Behind it, there's this principle called continuation, where context switching has much less overhead, and of course, the threads are released when they are performing non-blocking operations. Since they have no influence in terms of performance, in this case, well, it was obvious to us that coroutines was the best option. But this is not always the case. There are cases, of course, where we should actually choose virtual threads. And this is one particular case where we had a very specific requirement, not exactly this one. This is, of course, transformed. And what this requirement means is that we would have to send packages of 50 messages, only 50 messages at a time to 50 different users. And we had to be able to control that. And to do that, we also needed to bear in mind that this process was a fire and forget kind of process. So that means that we wouldn't care if the messages would be lost in the process. If by any chance one of the messages would fail, we wouldn't want the process to stop and we would have to continue sending messages. And that is how the whole thing went. There just wasn't really a need to control failures because the system was reliable enough, and on the other hand, not everyone needed to get that message. So this is the first solution we looked at. This is simply an implementation using Kotlin Coroutines. We are creating a suspend function and we are sending a message with 2 input arguments. The first one is the text of the message we want to send, and then we have a list of users where we are going to send the message to. As a first step, we create a coroutine scope with the default context, whatever is associated to the current coroutine, and we just chunk all of the messages in packages of 50. For every package, then we map that into a map of launched coroutines. How this works is, it is our package right over here. It is a package of 50 messages, and those messages are going to be sent via this function over here. I called it send email. It could have been sent message. I think more empirically, we just send emails when we are talking about sending messages. It doesn't have to be the case. The implementation is totally irrelevant for this case. So we send these, and we create another list of all of these asyncs together. If you recall from before, you know that async returns a deferred value, and that deferred value can then be retrieved if we await. So in this case, Kotlin has something interesting for us, and that is the await all that we can then apply to a list of all of the deferreds that have been generated by using this send email. The thing is, this send email is wrapped by this retry, and retry is a function that I have created to be able to send the email within the first 5 tries. If not, then this will fail. The 500 over there is the timeout, that is 500 milliseconds waiting for the response from the server. If we then do an await all, the execution will halt there until all of the coroutines have executed, and then it will move on to the next package of 50 messages. What is the problem with this case? It needs a coroutine scope. That is the first thing. We need to work with coroutine scopes, and we need to work with suspend functions. We have seen before an example where this was actually good. It meant that we could manage our coroutines in a structured way within a structured concurrency paradigm. In this case, that's not what we want. Essentially, we want to fire and forget and send these messages. There is no reason to make an organized call or to wait for another request or to wait for another coroutine. That doesn't happen here. It's just essentially sending fire and forget, and we're done. And so suspend and coroutine, all of these paradigms don't seem to make much sense if that's all we want to do. So then we find another solution that we found better to use, and that is simply using Java virtual threads. Now with Java virtual threads, we still do have to chunk the list of users. In this case, 50 users for every chunked bit. And then we map that in the same way as we did before. Only now we just start a virtual thread, and then we use the same function, this retry, to be able to send the email at least 5 times or until success. Otherwise, simply fail and never worry about it again. There is one catch here. We do need to make this for each and be able to join all of the threads for all of the different packages of 50 users in this case. So that means that although the code is a bit verbose, it's still better than what we saw before with coroutines. And the good thing about it is that we can decide launching this code either from a coroutine context or simply from another virtual thread. It is really a choice if we do it this way. And so there's no need for a coroutine scope, but now we wait. This comment is referring more to the idea of blocking, because we are not running send message in a virtual thread. And of course, for every single one of those users, we are sending an email. But send message doesn't seem to be part of any dynamics of synchronous or in coroutines or non-blocking. Well, that's not really a problem because that's now a choice. If we put this in a library, we can call whatever we want from that library however we want. As I said before, we can call this from a suspend function. We can call this from another virtual thread. It is really our choice. It makes it more universal, and it's very easy to read at this point how it's being implemented. And we know for sure that we are complying with the requirement, and that is sending 50 messages simultaneously every time for all of the users that are available on this list. And the message we are sending is whatever we put here on this text input parameter. But here's the thing. When we are choosing what we want to use for code, we also need to take into consideration what are the impacts in terms of performance. And so one of the things that I found interesting to investigate is how do these paradigms interact with each other, and how does that affect our services and how it affects how they work. So one of the things that I did was create first a Docker compose that I will use for every single test, and what this will do, it will halve the usage of the CPUs, and it will use a memory up to 270 megabytes. 270 isn't a lot, but what we want to test here is how a Spring application will work, because all of this that we have seen before needs to work, of course, in some kind of service framework, and for this case is actually Spring. And so The idea is to be able to test different forms of a Spring web application implementation and then see how does that respond and how can we see that in terms of response times, in terms of resilience, in terms of the capacity that the services have, in terms of how many requests can they handle simultaneously and how much can they resist back-off pressure. And the reason why I have halved the CPUs and limited the amount of memory available for each one of these tests is simply because I don't want to blow up my machine, because these tests are quite intensive. So as soon as I can have a conclusive result from the machine, the better. When I look back at the time that I was giving this presentation in London, someone asked me, and this is a question that I also had a while ago when I did a presentation for a company called Aonix, also with the term of reactive programming. The first question that I got is, these tests aren't reliable in terms of the machines that we are using, because these tests may behave differently in one machine or the other machine, and the idea was that I could get different results in different kind of computers. The behavior that we are having a look at in these slides and the demos that I'm going to show about the performance of the following different implementations of a Spring Web Service application have been tested in different machines. So that includes a Mac OS, that includes an Acer machine, that includes a Dell machine. These are all tests that have slightly different results, but the pattern is the same. And so the idea that what I'm showing now is a practical result for one machine, it is true, but it is a reflection of all the tests that I have done before. Bearing that in mind, it is important for us to see the behavior of our application when we have different implementations, because these are behaviors that we can easily replicate locally, whatever the machine you have. It's completely independent. It may change if you don't have enough cores. It may change if the memory is very limited, but I would say that if you have at least 4 cores and 2 gigabytes of memory, 4 gigabytes of memory, you will be able to make these kind of tests with the same kind of patterns and have these kind of results. To perform the tests, I use a tool called Locust, and Locust is a tool that allows us to make benchmark tests and allows us to make performance tests, and of course tests that will check if our application is resilient or not and how much capacity it has. In order to be able to start Locust, and I will show that in a minute, we need to have a file, Python code, that will execute whatever we wanted to execute per user that we configure in Locust. So the first thing we need to do is to create a Python code that is going to make a request to an endpoint called fulfillment. It will just be a GET request and it will be in JSON format. That is, the responses will be in JSON. And that's what we have right over here. So we have the endpoint that we are going to make these requests against, and then we say that we accept the responses in a JSON format. It's very simple, and the idea is simply just to make these GET requests. The initial implementation where I made these tests is this one. So in the slides we have the old implementation. It is just an implementation where I did not use a database. I simply logged information to the console and then returned products that I have created during the calls to these endpoints. And so in this first slide, we see that this is simply a traditional Spring MVC implementation where we find a getItems function that is implemented using a get mapping. And therefore, in our implementation, we find that we have a mapping of 1 to 10 that then will create different products. In this case, it's a TV from the aisle type room. And then we log the product to the console, and then finally we return its name. So this will just return a list of all of the TVs that we have created, in this case just 10. And this example will replicate throughout all of the different kinds of implementations that we will find of a Spring Web application. So this form is interesting. This is the old way. And there's a question there, or is it? This is exactly so that we keep this in mind. until the end of this presentation, where I will show the last implementation that can actually be much better than this one and looks just like this one. But first, let's have a look at the results that I got. And so with a ramp up of 1,000 users per second up until 100,000 users, I started Locust against this endpoint, and then I got to be able to perform about 2,000 requests until things started failing. 2,000 requests seems like a lot, but it's really not that much. And we can see that over here in this graphic, where we see at the top the effects of ramping up the number of requests per second to this service. And what happened here is that up until this point, the requests per second maintained the same. So the application had a strange behavior in which no matter how many requests I did, none of them would fail, and only these amount of requests would be successful. And the same thing kept going until at this point, just around 20 seconds, everything started, and so the successful requests went down quite a bit. So this had an impact to the response times, meaning that around here 50% of the requests were getting response times of around 3 seconds, and then it went really up until the 15,000 mark. And so here the requests took about 15 seconds to get a response back, and those were the successful ones because there was not an indication that the requests were failing. They simply kept going on up until here when I decided to stop the running test. So the traditional Spring MVC was a great pattern. It happened in 2003. It was good to read, but it wasn't that capable. It was not fast enough. And so it was an easy pattern to learn. It was a good 3-tier model. It had a model view controller, the domain model. Data transfer object was also part of that architecture, converters. This is something that we still are using today, and it will probably take a long time for us to stop using it. The problem is that not many were aware of the inefficient aspect of it. The inefficient only appeared when raising the load, but they were not enough when the capacity was a requirement for these services. Why was there a need to improve it? The idea was there all along. When comparing the performance of Spring for higher loads, Spring and other JVM-based solutions would fail to be on the top. And I'm thinking about things like implementing high-capacity services with Go, with other languages, but Spring wasn't as performant as other frameworks. But here is an important aspect of this test that I did for the presentation. It only considered creating products on the fly and replying back to the client with those products. It didn't consider the database. Here's what's also interesting to do. Let's create the first test challenging a database for it. And this is where I come up with the slight change in the project, which we are having a look at it right now, that will repeat for all of the examples that we are looking at. In our project, Virtual Thread Coroutine Cooperation, we have another module which is called Warehouse Fulfillment MVC, which is where the first tests were made from. Now we have a project that is a bit different, that is now covering the access to a database. If we look at the resource files and application properties, we'll see that it will try to connect to a database running locally. And there's nothing special to this connection. It's still just running the MVC model, and we are configuring here the JDBC access to it. The database itself is configured in a specific folder for it, and that is Docker PSQL. You probably have seen this in other projects. There is this original script that has been posted here, which is called create multiple PostgreSQL databases.sh. I've made a few modifications to it so that it allows us to use other files, data in schema, and therefore create our database very easily. And in the database, what I'm doing now is creating 10 different products that we will then use in our services to access that GET endpoint. To create a product, I'm just using a for loop, and in this for loop, the only thing that I'm doing is creating a sample product with the IL type room. That's it, and the ID is a generated random UUID, calling this method, which is recognized by PostgreSQL. The schema is the same as what we used in the previous tests. There is a product with an ID, which is UID, and the name and the IL type. To run this example, or any of the other examples, we need to go to the specific directory where they are. So this one, for example. And the best way is just to use the command line. If we go to the MVC module, we can then just call make, and make will simply build our jar that we can then use in our Docker container. While it builds, I can show you what that container looks like. The first thing, we create a Docker file that is using Eclipse Tamarin, and there we just make a copy of the jar file and just simply run it with this entry point. And this entry point has a java-jar warehouse fulfillment.jar. All of the other projects have a warehouse fulfillment.jar, so the Docker file will be the same for all other projects. Then what we do with the Docker compose file is simply start the fulfillment service and the Postgres database. The Postgres database doesn't have any limitations in terms of how it starts. It has an health check implemented so that the fulfillment service can wait until the database is ready, and then it will start running with these limitations of half the CPUs and memory up to 270 megabytes. Now the build is complete, so now we can just make dcup, and if we do this, the Docker Compose will start creating the different containers, and then it will run them the way I just explained. But before we continue with these tests, it is important for us to remind ourselves, what are these tests about? These tests are not about performance. These tests are not about any other parameter but resilience. And these tests are going to be run against different kinds of applications. We just saw an example of a graphic for a Spring Web application using Spring MVC. Just Spring MVC, a blocking application that uses the JPA framework to connect to the database. The second application is going to be also a Spring Web application, but it will use WebFlux. And WebFlux is part of a reactive architecture. And for it, we are using our 2DBC to connect to the database. The third application is the same, a WebFlux application, but it also uses coroutines, which means that instead of using Flux, we are going to use Flow, and instead of using monos, we are using Suspend. And for the fourth example, we are using a Spring Boot application fully implemented with Java virtual threads. But in order to be able to test these applications, we need to give more capacity to our containers, because we would not be able to work correctly with coroutines or virtual threads or even with WebFlux with half a CPU or with an upper bound limit of 270 megabytes for memory. And so before I was able to run these tests on this machine, I had to consider different variables. One of them is memory. So if we go here to Docker Compose, we can see now that the memory has been configured to be 1 gigabyte. We can see immediately also that the CPU is configured to be 4. So we are running this with 4 cores and with 1 gigabyte memory. But this is still not enough. For this particular machine, I also needed to configure something else, and that is the heap space. So this is where we create objects in Java. And the heap space for these tests for this machine ended up being optimal at 500 megabytes. And also 500 megabytes for the upper bound limit of the heap space. We will see differences in the different applications in terms of response times and in terms of requests per second. But most importantly, we are going to see the difference of how resilient these applications really are, and what coroutines can do for us there, and what virtual threads can do for us there. And also see the difference between WebFlux with just using the blocking model. Bearing that in mind, let's just start this first test. So the first thing we need to do is to start the containers. And while the containers are starting, another important thing to know is that I will run these tests with Locust. And Locust is, as we have seen before, this framework that we can then use to make several requests simultaneously to our services for each second. Each test will take about 4 minutes, and I have run these tests on other machines, and they always follow the same pattern. This is important to mention because we may have the illusion that these tests will only work this way for this machine. The parameters may differ, and we may have to tune that in if we use another machine than the one that I'm using here, but the patterns that we are going to see should repeat themselves whatever environment that you choose to run these tests on. So now the containers have started, and now it's time for us to run locust. To run locust, we can just run make launch locust. When we start this will start locust in the background. It starts a graphic user interface that we can access if we go to localhost at port 8089. And this is the graphic user interface of locust, and here we can configure lots of parameters. The first parameter is the maximum number of users that can send requests simultaneously to our application. In this particular case, I will choose 240,000. This will be replicated for all the other tests, and I will choose a ramp-up of users of 1,000. Why am I choosing 240,000? This is because I want to make a test run for 4 minutes. And 4 minutes means that we have 240 seconds that then multiplied by 1,000 result in 240,000 users. So that's why the peak concurrency ends up being 240,000 users. We will not get to that number on any of the tests because Locust can only rely on local resources from the local machine, and sometimes when the resources are not available, Locust does not increase the amount of users, and that means that it throttles the ramp up of users. We have a maximum of 240,000 users at peak concurrency with a ramp up of 1,000 users per second. We are making requests to our local host. The Python script that we have seen before is hitting that fulfillment endpoint, and we are running this test for 4 minutes. I will now run this test for 4 minutes. In your screen, this will take about 5 seconds. And when the test stops running, we will have a look at the results and interpret them. Later on, we will come back to these results to compare what we've got in the other applications. Okay, so the test has ended, and now it's time to analyze the results. So let's do that. First, I'm going to stop the test, and now we can have a look at this. Now we can see that our MVC application didn't took very well when the requests started being about 69,000 users. So when the load surpassed 69,000 users, in this case, our application started failing. Errors started being reported, and we can have a look at that right over here. We can see that there are about 21,000 errors at this point, and we can see that the application couldn't keep up very well with so many requests at the same time. But we also see right over here that it actually started failing earlier when the number of users were 56,000. Now we need to consider also that this is not strictly 56,000 users. These are the users that are configured by Locust at this point, but we need to take into consideration also that the application is already busy with requests from before. And that's why we get here requests that get response times of 10 seconds, 200 milliseconds, which is not bad, 240 milliseconds, which is, well, 240 milliseconds is bad as well, because the application is running in the local machine. And we have here also 16 seconds. There are quite long response times. The application isn't doing very well from this point onwards. But there's one metric in this graphic that shows that the application is actually doing well up until this point, and actually very well. And those are the requests per second. We can see that the response of the application is very quick. We can see that there are response times of over 8.7 seconds. At some stages, 9.6 seconds, but the requests per second are actually quite high. Here we can see also almost 1,000 requests per second. And even when it fails, we can see 1,000 requests per second, even more than that. And so something was going well with this application. It's just that the capacity couldn't keep up with everything. And so what can we conclude here? We can see that our application in terms of resilience isn't that great when it comes to MVC. It does perform well in terms of requests per second. And as we have seen before, when it is only about CPU operations with a very strict limit of CPU and memory, the application doesn't seem to run very well. And that's something that we can go back to the chart and see. So here we can see that when we were making requests to that endpoint where we were returning 10 different products back to the client, the application also didn't stood up very well if there was a limitation in terms of CPU and in terms of memory. And the reason for that strict limitation is because CPU operations, of course, don't need that many resources as input-output operations do. So therefore, we were able to catch, in this example, one situation where the application couldn't really keep up with a lot of requests. But this could happen also in the applications that we are going to test next, or not. This is the same example of that CPU-bound operation where we create products and return them back to the client. But this return back to the client now is made via Flux, because now we are looking at an example of Web Flux. And now we can have a look at the code and see, at least from the style perspective, what is going on. We see a small increase in complexity in this case. Why is that? Because we are using Flux, and Flux is something that we can use to return lists back to the caller. And when we look at the code now, we see something slightly more complex than the example before, which is pure Spring MVC. This has to do with this Flux keyword that now appears here. Flux is used to create something equivalent to lists, but in a reactive way. Flux is a publisher, and all of this framework is based on the observable pattern and is based on publishers. Another way where Spring Web Flux differs from the Spring MVC model is that it relies on Netty to run. So instead of having Tomcat, we use Netty, which is a server specifically made to be reactive and to work with these observable patterns and these paradigms. This Flux in this case is not connected to an R2DBC, there's no database connected, and we can now observe that. And Flux actually started a revolution about 5 years ago when it first came out, and it was very, very interesting to work with Flux because it allowed the application to be reactive, and simply implementing a lot of asynchronous patterns and observable patterns and the publisher pattern as well, as we have seen. It made it possible to use applications in a different way and make them more resilient. That means that applications could now resist more heavy loads and resist more being able to process multiple requests being sent simultaneously. But the big question was, how good was this and how efficient was to use this? It was very efficient actually. But the market for Flux didn't take off very well because programming it was not the easiest thing. However, Flux these days is still used a lot in applications that rely on a lot of input-output operations. However, its usage might see a decline because, of course, of Kotlin Coroutines and now virtual threads. But let's see how the tests turn out when I tested this application by making multiple requests to it, using the same ramp-up of users as we have seen in the first example. We can now see here that this application now was able to process in 27 seconds about 19,000 requests. And we can also see the pattern that this took in the charts that show the total requests per second. We can see that the application was able to be stabilized up until this point, up until second 26. And from that point onwards, it started failing. But the point here is that the application was able to resist a bit longer, and it was able to process a lot more requests. So this was better. Programming with WebFlux may not have been a lot better, but definitely the effects of efficiency and in terms of resilience were also better. Spring WebFlux with reactive programming paradigms was released in 2017, and back then I made an example about it called C Shell Archiver. It's a bit of a goofy project, but it allowed me to explore the paradigms surrounding Flux and Mono, and it was fairly complicated to implement things, especially using zip functions. The way to test Spring WebFlux at the time was using Blockhound. This project uses block count to test if certain endpoints are reactive or not. Reactive programming with Spring Web Flux meant that we were using Flux and Mono. In the example, we saw a Flux example. Mono uses one single element instead of an iterable. And as I mentioned, Flux is used for collection, Mono is used for instances. It has good support for R2DBC, good support for Spring, and the observability pattern and publishers were visible. And the reason I mention this is because the following implementations or so-called other reactive alternatives like coroutines and virtual threads don't really use this. They don't really follow observability patterns, and publishers are not really that visible. What is the problem? Coding, as I mentioned before, would get extremely complicated, particularly zipping functions. So let's first have a look at the implementation using Spring Webflux. In our project, the Webflux project is located in warehouse fulfillment dash, of course, Webflux. So let's have a look at what's in there. If I go over here, then I'm already in the command line for the Webflux project. But we can go here to the main folder and then come here to the controller. And here in the controller, we have a similar implementation to the one that we saw on the slides, except that here we return a list of products that are returning from the database. And this find all is an implementation of the reactive CRUD repository find all. And this is something that is available in Webflux. So we are retrieving all of the products in a reactive way. As you can see also here, we can get the item if we want by using Mono. This get item by ID returns a mono of the product that we are returning back to the caller, and that product is found by using this find by. That is a method that comes out of the box again from the reactive CRUD repository, which is this one over here. Also important to mention is how this application is configured. The way to configure this is by going here to resources, for example, and then configuring the database connection this way using the R2DBC parameters. These three R2DBC properties come from the R2DBC data library from Spring. We need to add this to our build. I can show you that. It's over here. This is the Spring Boot started data R2DBC that we need to configure the connection to the database. But for this to actually work, we also need the driver, and the driver is this R2DBC PostgreSQL. Of course, this is just the alias. If we go to the TOML file where this is declared, we can see that this is the R2DBC PostgreSQL driver with version 1.0.5.release. And to make it more clear how these tests are being made, we also need to have a look at how the database is being built. I have mentioned before that we had 10 products. Well, we have 10 products in our tests that were created before this that I used for the creation of the slides. But with the current data, we are adding 1,000 products. And this is to create gigantic payloads so that we can test our applications and see the difference a bit better between the different kind of implementations. Now, having that out of the way, we can already start our test. And to start our test, we need to go here to the command line. And here, what we should do is start the containers again. But I have created another script which is located in this makefile mk, and it is called dcup rebuild. And dcup rebuild will try to stop all containers related to this project. And the way it looks at that is by using the names and using this Postgres. So if you have any Postgres databases running on your machine with the name Postgres for the container, then please be aware that that is what will happen. It will remove the image and the container running. So inside the Webflux folder, what we need to do now is to start the containers. And to do that, as I mentioned, we just do make dcup rebuild. And this will stop everything and restart the containers specific for Webflux. And we see them already here with the name. And now we have to start our Locust service. And so we just launch Locust. Now Locust has already started. And in the same way as I did the first test, I will now run this test for 4 minutes. Let's prepare it right over here. and let's say 240,000 with a ramp up of 1,000 users, and this will run for 4 minutes. And as I mentioned before, for the first test, this will run now for 4 minutes, but you will see this at a much faster pace in 5 seconds. And then after the run is complete, I will get back to comment on it. So let's start. So we've got our results from the tests against Webflux. So this is our chart from the tests against our Webflux Spring application, and we can see that from this point to this point, the application was quite stable, but there is this bump over here, and then there is no more problem to this point over here. So in general, we can't say that this implementation is way more resilient than the one using Spring MVC. But one thing that it's curious here is that if you notice the requests, they are made much slowly. So the successful requests have a rate of much lower values than the one that we saw in MVC. So these are around 100, 200 requests per second that are being successful. And in the MVC chart, if you remember, we had around 600, 500, 400, and it used to variate through these numbers. But here we are only reaching peaks of 326, 312, and here at the same time we are getting errors. And if we check on the failures, we can see that these are all failures because the service is too busy to respond to more requests. And here in the statistics, we see that it was able to process correctly around 40,000 requests, which is a lot more than the 11,000 requests that we saw with Spring MVC. So what does this tell us between Webflux and Spring MVC? Well, it tells us that Spring Webflux seems to be more resilient, and it seems to hold on to more requests at the same time than using Spring MVC. And of course, this is only one test for one machine. I was actually expecting not a single failure using Spring Webflux. This could be because I've adjusted the variables that I mentioned, the free memory, the allowed CPUs to use, which are 4. So we have 1 gigabyte of memory, 4 CPUs. We are using 1,000 products per request in the GET request. We are also saying that we have 500 heap space, 500 megabytes heap space per each one of these containers. And so perhaps to solve this bit, I would only have to raise the heap space. But the idea that I want you to have with this chart is that Spring Webflux is more resilient than Spring MVC. But it's not perfect, of course. And remember that these variables, all of these parameters that limit the usage of the resources on this machine are also on the edge. So this means that any of these applications can all of a sudden present some erroneous behavior, which is okay, as long as we can compare, in a way, the resilience between the two different applications. And if we go back to the diagram of before, with the same Webflux, but in this case without a database, we can see that in the graphic that there is more resilience to it, but in any case, some errors have occurred anyway, which is kind of what we have also reproduced in this case, also with the database, and with a bit more capacity, 1 gigabyte memory, 4 cores, and 500 megabytes of heap space. So they kind of match each other when they are CPU bound operations or input-output bound operations. They seem to match when it comes to this behavior, that one is more resilient than the other, and yet they can fail if they are subject to too much back-off pressure. But now it's time to have a look at this same implementation, but with Kotlin Coroutines. It is quite similar, but in this case, what I am doing here is using a flow of. And flow of does the same as I did with Webflux. It is creating a flow from a fixed data. But let's focus on this for a moment. When we use iterators and wrap them with flow of or with flux of, what happens is that we are breaking, in a way, the reactive capabilities of Netty. So Webflux, with or without coroutines, will have a performance decrease and might also suffer a bit in terms of capacity. But in any case, these are valid tests in terms of purely CPU operations, which means in this case just creating 10 products and giving them back to the client. The flow is programmed just like Flux, but the backbone is now made with Kotlin Coroutines, and it works with the assigned dispatcher by Spring. The main difference between one and the other is that Webflux, as I mentioned before, works with asynchronous processes and implements this observable pattern and uses publishers like Flux and Mono. In this case is different because we are just using the power of coroutines, and therefore everything is coroutine based, potentially leading to better results. Or worse results. It entirely depends on the hardware being used and the software being used. And so when I submitted this endpoint that returns 10 products on the fly to the client using a Webflux application with coroutines implemented on it and using flows, I got these results. I got 130,000 requests in this case, so that's already 10 times more than what purely Webflux allowed me to do. And another thing is this bizarre behavior where although I am increasing and doing a ramp up of 1,000 users per second, from the beginning to the end, the application never failed. And this is an application that is limited to half a CPU and to 270 megabytes of memory and the default heap space. These are all very low values and they limit a lot the execution of an application, and yet nothing failed as the application went along, which accounts for the huge amount of requests that were processed successfully during this time. And if you look at this time, it starts at 9:10:43 and it finishes off at 9:13:43. So for 3 minutes, the ramp up kept on going. So these are really a lot of users that could continuously make requests to this application. Well, it is true that the payload in this case is very small because we have only 10 products and each product has very few fields. And this also means that processing these requests is very easy. There is no database behind it. And therefore, it is also very acceptable that no request was lost during this ramp-up time. This behavior might be different when submitting this to a database. But before we get into that, let's have a look at the summary. Why should we use coroutines? Now, Kotlin's inception year was in 2016. Coroutines allow for the scope creation instead of a specific structure concurrency block. Scopes are important if we want to provide an elegant way to cancel, for example. And cancellation using structured concurrency with Kotlin coroutines is much easier, as we have seen before, than with Java virtual threads. Coroutines have a non-preemptive scheduling architecture behind it, which allows for graceful shutdowns. There's a better use of resources. It still allows for concurrency. They possess the additional benefit of parallelism, and we can specify the dispatchers that we want to use. These dispatchers are also referred as the context. We can also define the name of the dispatcher if we want, and we can alter different properties of these dispatchers. The point is that when we select dispatchers in Kotlin coroutines, we are specifying which one of the specific coroutine dispatchers we want to use. Kotlin coroutine dispatchers have got 4 major dispatcher types. One is the I/O, specific for input-output operations, the default, which is specific for CPU-bound operations. Then we've got the unconfined, which is used for whatever thread is available. And then we also have the main, which is specific for Android applications. There are more dispatchers, like for example the Java virtual threads dispatcher, where we can also run coroutines on. We will also have a brief look at that towards the end of the presentation. But for now, let's now test this same thing but against a web application that is connected to a database and has Webflux in it, R2DBC, and crucially Kotlin Coroutines. In our project, there is one module called Warehouse Fulfillment Coroutines. That's where we want to go for this test. So we just go to Coroutines, Warehouse Fulfillment Coroutines. And now to start the application, we should just do a make decup rebuild. But before we do that, let's first have a look at how exactly the application looks like in the code. So if you go here to the get mapping, we see that there isn't much difference between this and what we have seen before, except that we are not using flow of, or we are using flux, or we are using any special types. And here we don't see any complicated code as we have seen before. We don't see any flux, we don't see any special declaration for it. And that's because, well, Kotlin allows that, but we are actually returning a flow of products, just as before. And then here we have get items, which is the definition of the endpoint, a get mapping endpoint, where we then get all the items from our database. This fulfillment service is a reactive service that it is now using a reactive repository called coroutine repository, which is slightly different than the reactive repository as we have seen before in the example of Webflux. In this case, I'm not specifying here the type. It is a flow, as we can see over here. It's a flow of products. And if we go inside get all items, we see that all the items are coming from product DAO and then find all. What is product DAO? It is this one over here, where we see that it is a coroutine CRUD repository. And that only means that this repository is implemented with the use of coroutines. And under the get items, we see a suspend function of get item. This suspend just means that this function is suspendable and that it can be used by a coroutine. And this only works if the object that we are returning is simply an object. As we can see here, get item returns only a product and not a list. If we want to return a list, we always have to return it in the form of a flow for this to work correctly and in a reactive way. And here we are getting the data directly from the database, and that means that everything is fully reactive. For now, just to recap, we are starting these containers with a 1 GB reserved memory for our fulfillment service, which will also have 4 cores reserved to it. The service will start with 500 megabytes of heap. We will run this test for 4 minutes, which again you will see running on a faster pace for 5 seconds. And then after the tests, I will analyze the results. For now, let's just start the containers. As you know, in this case, we do a make decup and then rebuild. And this should start our container environment with the database and the new service. And remember that our database at this moment has 1,000 products. So let's start locust, make launch locust. And now the service has started. I will now open the web browser. And this is the user interface. Let's put 240,000 as a maximum number of users at peak concurrency. 1,000 users ramp up per second, and we'll let it run for 4 minutes. So let's start it. Alright, so this web service with coroutines has already finished, and I can see here exactly the same pattern as we saw with just Webflux. The interesting thing here is that there doesn't appear to be a difference for this specific case that would say to me that coroutines would be better than Webflux or vice versa. It just seems to me that this specific environment that we have, and that includes architecture, that includes the way we've set up our code, that includes the entities that we are using, it includes also the payload. It seems like everything is the same. So It seems almost like we can choose either coroutines or either Webflux, depending on what kind of code do we like best. It is difficult to argue against the argument that Kotlin coroutines look much better than the code implemented purely with Webflux. Flows seem to have much better semantics in the code, but again, this could be misleading. These graphics could be misleading because this is just for this application. And this is just one graphic. And probably this has more to do with a particular case where we are limiting the resources that the containers can use. But in any case, we can see that in the same way as Webflux did, the application is more resilient in that we get these peaks of failed requests, but the application resumes. Whereas in the MVC service that we have seen before, it started failing and it kept on failing up until the test stopped at the 4-minute mark. But let's break it down what it means to work with coroutines. Now, coroutines have gotten their compatibility with Spring in 2019. Coroutines claim to be simpler than Flux and Mono. That is true. Instead of Mono, we started using Suspend. Instead of collections, we started using Flow. The rise of the usage of channels, hot flows, cold flows, and there was talks about removing Kafka, RabbitMQ, and major dedicated data stream networks. What is the problem here? Coroutine complexity was still considerable when using structured concurrency. And because of the non-preemptive model, all functions and its instances would have to be marked as suspend. Otherwise, we cannot use them for coroutine purposes. And because of the non-preemptive model, all functions and its instances would have to be marked as suspend. No simple function could call suspend. And many developers still try to use suspend with a returned list or even with flows, in some cases also with Flux. What this means is that if we use suspend in combination with a list, that's just not going to work. It won't work. If we want to return a list, as I mentioned before, you have to return via a flow and not in a suspend function. But it has revealed many times confusing when using this in code, and we do see this confusion quite often. But let's now focus what it means to work with coroutines. Well, coroutines, this is something that I took out of my article that it's called Good Story. At the end of the slides, you have the links for it, and I will put this in Scribe, the updated version. And we see here 3 threads, and these 3 threads are what we call carrier threads. And carrier threads are threads that are available for coroutines, and they are, let's say, at coroutine disposal. So coroutines can use these threads when they are available, and then they can also release them, which is kind of what I have implemented here. This is kind of a map where we see time going in this direction, and we see that at some point in time, thread 1, thread 2, and thread n, they are all busy with coroutines. In reality, they sometimes are available, of course, but this is just a way to map the way coroutines would behave inside a thread. And the idea here is that coroutines can switch context, but with much less overhead than what would normally happen between threads. When we talk about virtual threads, we are actually talking about lightweight threads because they look like that in the code. We can program them in the same way as we do with threads. And the idea here is the same. They start using a thread, they take control of a thread, they release control of the thread. Actually, the JVM releases the thread, which is why it's called preemptive. So the virtual thread makes use of a carrier thread until the point that it needs to make a blocking operation. And at that point, that blocking operation means that the virtual thread will release the carrier thread, and the JVM will allow that thread to be reused by another virtual thread. We can activate virtual threads in our Spring Boot application if we do something like this. All we have to do essentially is to activate this flag. This is Spring Threads Virtual Enabled True. And if we do that, our virtual threads are activated. We can also try and do tests with reactive applications, but virtual threads will probably work better in servlet-based application servers, like for example Tomcat. If we do servlet, then that means that we are using Tomcat. If we do reactive, then that means that we are using Netty. The combination between virtual threads and Netty, which has a completely different paradigm oriented to reactive programming, might not work very well, but you can try. I tried that myself. I didn't see particularly any problem, but it's better to do this way because this is how it is predicted to work. And so our code with virtual threads will look something like this. Do you remember this code from the beginning of our presentation? If you didn't, let me remind you that this code looks exactly the same as the code we've seen before. It doesn't just look the same, it is the same code. It's back, and now we are back to the old model. What is happening here is that with the advent of virtual threads for Spring Boot, we can now simply activate that flag, and Spring Boot will work out of the box with virtual threads. However, there are issues with this. And the main issue that we have with this is that if we think that we can use virtual threads and not have to worry about anything else, we might want to be more careful with our code. Because, for example, Spring Data JPA uses a lot of blocking paradigms. And what that means is that we are actually using a virtual thread and not just a system thread. When that virtual thread hits the JPA library, when it starts using the JPA functions, it will start using a blocking model. And this is where certain discussions about using reentrant lock arise, because the chances are that when the virtual thread goes in through that, it will get pinned to a thread, leading up to unpredictable behaviors. I will explain later in this presentation those unpredictable behaviors, and I'll share some information about what is being said at the moment about those problems and those issues with Java virtual threads. But first, the example that we have just seen. The example again is returning 10 products that were created on the fly, no usage of database, just returning back to the client the whole list, and now it's just using the old model. When running these tests, it was incredible to see that the same kind of graph was generated pretty much in the same way as the Webflux graph was generated with the use of coroutines. And this can give us the idea that Java virtual threads can be used straight out of the box and without any problem. The thing is, it works out of the box in this case because, of course, I'm not using a database and I'm not using any library behind it. It's just simply a few operations with products and then returning them, and that's it. That's why it works so well. And Java virtual threads have the potential to do a lot of things. They started as Project Loom with fibers in 2017, and they were released with the JDK 21. This, according to what I could gather on the internet. Virtual threads turn everything on its head for Spring because they seem to give the promise that we won't have to use any more complicated code. So we won't have to be using suspend functions, we won't have to be using flows, we won't have to be using flux. It's just simple old code that everyone understands. That is the promise. It might not be just in the near future. There is no keyword or special objects needed. As I mentioned, the application stays reactive. It stays reactive in a way depending on what we understand as reactive. All of these things are now being called reactive. Virtual threads benefit from a preemptive and non-preemptive scheduling form. It is strange, but it is the Java virtual thread that decides when it should release the thread, but it's the JVM that does that for it. That schedule means that we can allow to virtualize threads in code that goes back to the imperative form without the need to be forced to make major decisions. The use of scopes is off the table and not needed anymore. What is the problem? Structured concurrent support is still very verbose. We cannot cancel gracefully the different tasks that we can spin out of a scope. Many frameworks surrounding Kotlin, like Project Arrow, rely on coroutines for their features, and this is something that virtual threads do not have. Streams, channels, and flows offer full coroutine support, but that is easy to do in Kotlin, while it is very cumbersome to do that in Java. Creating mobile applications, namely with Android, still uses a lot of coroutine. These are virtual threads. But how about how does this behave now with a database? I did mention just a few seconds ago that using the that using Spring.jpa might be a problem with Java virtual threads. Well, I didn't want it just to say that. I actually did a test for it. And we are going to do that test just now. If we go to our project located here, and we open this module, Warehouse Fulfillment VT, we can then find the source code and the controller over here. And in this controller, we can then see that the code is pretty much the same as we are used to doing for Spring MVC. Here we see that we return a list of products, and here we just use a simple product DAO, which is just a JPA repository. And if we look at the dependencies, what we have over here is just Spring Web, .jpa, and all of the things necessary to run Kotlin. We got the Postgres driver, and there is not much more to it. And if we go here to application properties, we see the normal definition of a database, and of course we see that virtual threads are now enabled. So how do you think this is going to behave? Well, we can just test it and see how it might behave. So let's go to the VT project right over here, and now let's start it. Now we all already know how to restart the containers and to start the VT application. Alright, so now the virtual threads application has now just started, and now we just have to launch Locust. All right, let's start the test. So these are some interesting results, aren't they? We can see that it started well, but then all of a sudden we've got a rate of successful requests and a rate of failed requests. We also see that the response times increase. There are some hiccups here, but in general, this worked pretty bad with Java virtual threads. And remember what I've said before, that there could be issues between virtual threads and the JPA architecture. So when we use Spring.jpa, we are essentially using a framework that relies on a lot of blocking principles. And so the combination seems to not be a great one. Another thing that it's important to notice also is that we have a limited system, and that means that we start this container with a maximum of 1 gigabyte free memory and 500 megabytes of heap. It could be that these limitations are influencing how virtual threads work. We could increase it, but even if we increase it and we see that virtual threads then start behaving better, it would still defeat the purpose of using virtual threads in the first place. We want a system that is resilient. Even if we try to make a vertical scaling by increasing the amount of CPUs or by increasing the amount of memory, that is still something that we shouldn't do if virtual threads would make our system more resilient. Of course, if we increase any of those properties, our system will be more resilient because it has more memory available and it has more resources available. The whole point of virtual threads, coroutines, and everything else is to use the resources that we already have and maximize their potential, which was not the case as we have seen here. But these, of course, aren't readings to say that virtual threads are not a good thing. I believe that they are an amazing thing, as we have seen in the example purely with the products being given back to the client and being generated on the fly, just a purely mathematical operation, nothing really related with input and output. These tests could have continued further, but then we would have to go to we would have to think of alternatives to Spring when it comes to data handling and accessing the databases. We would have to pick one of the data frameworks that would have to accept blocking operations and outside of the world of Web Flux, because that would not work with virtual threads. because it would probably not work very well to use virtual threads with Netty, which is the server that is needed to be able to run anything coroutine or Webflux related. And the reason I am convinced that virtual threads will work with a suitable data framework is that, as we have seen in this chart, the flow of data kept going. We were able to keep on making these requests. I would be able to make these requests by increasing 1,000 users per second for each one of these requests. And we see that Java Virtual Threads could actually deal very well with this amount of data and these amount of requests. But this whole testing reminded me of an exercise of last year where I wrote an article called Good Story about comparing coroutines and Java Virtual Threads. And in there, one specific test that I made was launching coroutines via the Java Virtual Threads dispatcher. And the Java Virtual Threads dispatcher is something specifically made to support Kotlin Coroutines in the Kotlin Coroutines library. And going back to the diagram that I created about virtual threads, where we see the carrier threads over here and the virtual threads making use of these carrier threads, we can think of running coroutines in a virtual thread this way. And what we see here is the carrier threads being segmented in different ways. What it means is that when I launch a coroutine 9, for example, using the virtual thread dispatcher, it can so happen that I am using that coroutine on virtual thread 1, which is going to be used on carrier thread 1, and then it might be used again on carrier thread 2, or again in carrier thread 1, or even in carrier thread n, whatever the carrier thread available is. The whole point is that the virtual thread maintains, so C9 is only one coroutine that then can continue its execution somewhere else. And then we have, for example, C5, which is being distributed pretty much everywhere. It's being used here in virtual thread 1, and it's being used in virtual thread 3. The idea is that the virtual thread dispatcher will then distribute the coroutines, will multiplex them on virtual threads instead of system threads, which is a multiplexing on a multiplexing. And the code to make this kind of multiplexing is something like this, where we create a new virtual thread dispatcher and we use this as coroutine dispatcher to convert it to a coroutine fashion like dispatcher, and then we can use it with flow on, or for example when we simply create a new coroutine scope and we have to specify which kind of context we want to create. In this case we can, for example, create a context that will use executors.new virtual thread per task executor as coroutine dispatcher. It is quite an odd construction, and the thing is, does this stand? Will this have any use? I made a test anyways, but for this one we are not going to make the test against the database. We are simply just going to leave it here, because when I saw that limitation with the virtual thread dispatcher, then it didn't make any sense to continue to pursue the results of a possible interaction between a Spring Boot application with activated virtual threads against a JPA database. It would also not make any sense to do that against Webflux, because then we would have Netty, and that would not be the right way to use virtual threads. And so it was very limiting, and I would have to use another data framework that would be more suitable to use with Java Virtual Threads. This one in specific, I didn't got anything good from the experimentation in my local machine against that simple method that creates 10 different products. In this case, the graphic looks like this, which seems like it failed very quickly right off the bat, right at the beginning. But this is just one case where the Java Virtual Threads dispatcher with coroutines doesn't seem to work very well. But I have one example where it actually worked really well. And that is not even using any input-output whatsoever, not even on a request level. This comes out of a project that I created, which is called Good Story. And this project is a project that explores virtual threads combined with Kotlin Coroutines. In 2023, there were a lot of blogs released and a lot of comments and a lot of posts. everywhere about this possibility of using the virtual thread dispatcher. It was a different perspective on threads with potential benefits. I never used this in production, and maybe this is not really an improvement. Testing is essential and benchmarking is essential so that we can make adequate decisions. But going back to this good story article, these were the results from that good story article. And what we see here in the left column is when I perform these tests. Then on method, I have the name of the algorithms that I used. As a short introduction, good story is a story that I created. It's a big text that essentially has a lot of words. Maybe you'll like the story, maybe not, I don't know. And what I am applying there on that text is different sorts of algorithms with different kinds of time and space complexities. The idea was then to perform 10,000 repetitions per algorithm and then see how long that would take using Java virtual threads, using Kotlin Coroutines, and then using the combination, which is what I call here Kotlin Loom duration. And as we can see on the right column, after all of these tests have been made, we see that there is a general improvement in performance when I use Kotlin Coroutines on top of a virtual thread dispatcher. Somehow this went a little bit better. Is this a conclusive result? It is fairly conclusive in the sense that on that project we can run this several times. We will see that what I call here duration, which is actually the execution time of each algorithm, will always follow the same pattern. So that means that between Java virtual threads and Kotlin Coroutines, there wouldn't be too much of a visible difference because these can vary quite a lot. But the duration of these algorithms in Kotlin Coroutines on top of Java virtual threads seems to point out that doing it this way, all of these algorithms simply execute faster. But again, everything that I've done throughout this presentation are all tests that you can do at home as well, and you can do also at your workplace or anywhere. I guess the important part here, and what I want you to remember from this presentation, is that we do have 4 different technologies that we can use, and then a 5th, which is a combination of 2 of them. We can use Spring MVC, we can use Spring Webflux, we can use Spring Webflux with Kotlin Coroutines, and that is with coroutine flows. We can also use Spring Boot now with Java virtual threads. And there we may need to change the way we approach data in our database by using suitable data libraries. And the 5th option, which is using a dispatcher that will make use of Java virtual threads as the carrier threads for Kotlin Coroutines. Now, which one of these options is the best for you? It really depends. But in general, the way we can see it is a bit like this. If the process is highly dependent on just access to the database, you may want to stick to just the typical MVC model. If it's performing many operations also, and it is also using different kind of calculations to get to the database, maybe a reactive option is the best. And it could be any of the 2. And if you want readable code that is not too complicated to program, maybe you want to go for Kotlin Coroutines. And finally, virtual threads. If it works, and if you see that everything works, perhaps virtual threads is the ideal option. Although I wasn't able to replicate any case where that would work simultaneously with a database access. But I've also explained why. It's all about getting the correct data source. As a conclusion, what can we take out of this presentation? Essentially, virtual threads are very impactful because of their support by the Spring framework. They are easy to use and build code with. Maintaining the code is easy, and it can be used in fire and forget scenarios, structured concurrency in both Java and Kotlin. Coroutines will still be used because of how well and elegantly they adapt to other paradigms. With coroutines, we can implement flows very easily, channels, event streaming, server-side events, and it can be used in both Java and Kotlin, but they are not prepared for Java and can get highly complicated that way. There are implementations of Kotlin coroutines in Java. I invite you to find those on the internet. They are fairly complicated, and I don't recommend to use that in Java. Instead, the best option. If you want to stick to Java, then use Java virtual threads. In any case, both can be used with similar or purely equal performance markers, leading to choosing them on the basis of code style, patterns, and design. This is true if virtual threads are correctly used. This is true if we are using Java virtual threads on Spring Boot. We just need to make sure that the flag that I shown before is active, is set to true, and that we are using the non-reactive version of Spring Boot. So that option where I mentioned which kind of web application we have, that should be servlet in that case to use Java virtual threads correctly. We can also try always to use the reactive version and see how that works with Netty. But I would at this point just stick to using the non-reactive version when we are using virtual threads, because the idea is to create code without thinking about these concepts surrounding Java virtual threads and Kotlin Coroutines, which are continuations. We just want to create the code as we did before, with an added advantage of it making use of Java virtual threads. Java virtual threads have a definite future, but for Android at the moment, only up to the JDK 17 is supported, and no support is available for Java virtual threads as a result. Kotlin Coroutines will stick around for Android for a long time. In Java server side, the use of Kotlin Coroutines may go down for simple applications, and only where certain specific operations are needed will Kotlin Coroutines still likely be needed due to their simplicity. And what I mean with this sentence is that if the code gets too complicated, then Java virtual threads are no longer helpful, because they can get seriously complicated. If you remember from the first few slides when I showed the differences between using Kotlin Coroutines and Java virtual threads for the first two examples, that is what I mean here. If we are getting code that is getting somewhat complicated, then Kotlin Coroutines may actually make the code simpler. For all operations related to structured concurrency stream and event handling, the usage of Kotlin Coroutines may actually increase, as is the case with mobile applications in Android. This is true. Android makes massive use of Kotlin Coroutines at the moment. Since Kotlin was released and since it's available to use in Android, essentially almost all applications are now being developed in Android. And that is because of the potential of Kotlin Coroutines. How will that look like in the future if Java virtual threads ever get available for Android? It's difficult to tell, because every single paradigm in Android is really highly dependent on how Kotlin Coroutines are built. Maybe Kotlin Coroutines can one day not be used anymore, given the potential of Java virtual threads, even in the case of Android applications, but that isn't anything for the near future. In fact, Java virtual threads at the moment are difficult to use, precisely because the idea that we only have to activate that flag and simply use the servlet application type isn't really working that well. And it's important now to have a look at what I mean with that. There are lots of blogs and lots of articles on the web about this specific problem. And I can show you one that happened in my personal projects, but also in my professional life. In this article by author A.N.M. Baslur Rahman, the author talks about how to diagnose and mitigate pinning in Java's virtual thread execution. Here's the thing. This problem, thread pinning, is very real. If we are making calls in our code that will make use of synchronized methods, or that will make certain calls to native methods, or they are part of some kind of blocking architecture, odds are that the virtual thread will be pinned. And by thread pinning in this case, what we mean by a virtual thread being pinned is that that virtual thread will no longer be released. That virtual thread is now attached to a system thread, and it works just like a system thread. It is blocking, it has all the inconvenience of a system thread. And so what the author talks here about is how do we mitigate those issues. So as we scroll around here, he talks about what is spinning. So in the context of virtual thread, spinning refers to the condition where a virtual thread is stuck to its carrier thread, the platform thread on which it runs. When a virtual thread is pinned, it cannot be unmounted from its carrier, effectively monopolizing that carrier thread for the duration of the pinning. So that also means that the potential for errors is much higher. And there are two suggestions here. Pinning occurs in two main scenarios: synchronized blocks, native methods or foreign functions. And it talks about mitigation pinning. One of the things that it talks about is the usage of re-entered logs to mitigate the situation. I tried this, it didn't work in my case. And then there's a code review, which basically talks about removing the synchronized blocks. Another thing that it's also important when we detect thread pinning and things go wrong is really think about the usage of another library. In this case, I'm using the Spring Data JPA, and odds are that because of thread pinning, then there is an excessive usage of memory and things go wrong. And this is only my opinion of what could happen to Kotlin Coroutines given the release of the JDK 21, where we can finally use Java virtual threads. In my session, I got very interesting questions, and one of them, as I have mentioned before, was about the scientific approach of what I did here. Now, the idea wasn't really per se making something terribly scientific. The idea was more to check if I could reproduce in local machines the patterns that we see all over the internet and what is being discussed at the moment. I think I was able to reproduce that quite well in my local machine, but it wasn't just my local machine where I tested this. I also tested this in other machines. I also tested this, for example, in the Mac OS. This is a SARE machine, and I saw these patterns everywhere. But the whole point was really just to have a look and see in real time how these things can affect the different kinds of ways to process data in different machines and with a Spring Boot service, and also using different implementations. And I mean the Spring MVC, Webflux with coroutines, Java virtual threads, and potentially Java virtual threads used as carriers for Kotlin coroutines. Another interesting question that I got was, is it just about activating that flag to enable Java virtual threads? Yes and no. Well, what is happening at the moment is that when we activate Java virtual threads, then Spring Boot will automatically activate virtual threads, and that means that although we don't see it in the code, those endpoints will be called with a virtual thread. And so if we try to get the name of the thread in runtime, we will get a thread that is called virtual thread, and that will confirm that it is a virtual thread and not just a normal thread. The problem is that we can simplify what we are saying by, okay, we activate virtual threads via that flag. The problem that will arise is when we deal with other libraries. If those libraries aren't prepared to work with blocking operations, then that will only increase the likelihood that the virtual thread will get pinned. And if they get pinned, they will behave just like a normal thread, which is not what we want. And so, yes, we have to activate that flag, but we also need to worry about the libraries that we are using. That means that, for example, as we have seen before, the JPA library will probably not be a good idea because it seems to have a direct impact on the way virtual threads are supposed to work. And as we have seen in our tests, it requires something else. I actually did tests outside of this presentation where I simply increased the heap size and the available memory, and then I was able to get better results. But that defeats the purpose, of course, of using virtual threads. The idea is that we can make better use of resources and make our services as resilient as possible. And it is also true that with vertical escalation, by increasing CPUs or memory, we actually always get better resilience. The idea of using these new technologies is precisely to increase a web application's resilience by not doing that, by not doing a vertical escalation of our resources. At some point in the presentation, I also made a question, and that was, has anyone ever used virtual threads before? And the room was silent. And the good reason for that is that we still don't know very well how to use virtual threads. As we have seen in blogs, there are issues when using virtual threads, especially when coupling with other systems, with external systems, or with another library. So we need to make sure that we use the actual library that will be compatible with the usage of virtual threads in order to make everything work as we expect. We did see that virtual threads seem to offer a lot of promise if we don't use any external database, if we don't use any extra library, if we just use simple business logic in our service and don't use any external libraries. We are almost 100% guaranteed to get better resilient services, as we have seen with the example where we had half a CPU and only 270 megabytes of memory. At some point, someone pointed out to me that I didn't make any example about Android. Well, the session was getting too long. This was supposed to be a 45-minute session. This presentation is, of course, longer than that because I also did the practical examples as an extra, but it wouldn't fit in the session. However, I can now answer that question over here. And so if we go to our example project and find the warehouse fulfillment app module, well, that module is an Android application. And what I did is a very simple application just to illustrate another example that would match the first example we saw in the beginning of this presentation. You remember we had posts, comments, and the user, and we were trying to fetch all of that data in an asynchronous way and put that all in a process data object so that we could then store that in our database, for example. But in this example, we are looking at an application that has 3 fields, only 3 fields and nothing else, and it will display the name, the post, and the comment in an Android application. And the way it does that is, of course, in this case using Material 3 and using Jetpack Compose. And what we have over here is a name, a post, and a comment. And as you can see here, I'm filling in those values via coroutines. And these values are name, post, and comment. And they are all outline text field. Now, we can look at the way the application looks like at this point. Let's call it build and refresh. And this is the preview of how the application would look like. And it's just made here via Jetpack Compose in this preview. And we can see here that here's my name, this is my first great story, and this is my opinion of that story. And here we have what we have filled in that data. Now, the idea, we can edit these fields, of course, these are text fields, but the purpose of this is to illustrate that we can also use coroutines in Android, and actually this is the default way now, currently in our days, to fill out these fields in Android applications. And of course, for more complex applications, we will have a much higher and more intense use of Kotlin Coroutines because they can spare a lot of processing and they can spare a lot of resources when when working in an Android mobile phone, which typically has less capacity than your ordinary laptop computer. If you reached this point of the video, then congratulations. Now you have a different perspective on how to work with these 4 kind of options for Spring Boot services. To be clear, with this session, I am not making any definite conclusions about if MVC or Webflux with Kotlin Coroutines or virtual threads is the best option in general. There is one best option in general for each specific case. Your typical Spring Boot MVC application may have less resilience, but in the example we looked at, it actually processed the requests much faster than Webflux in any of the 2 implementations. Using Spring Webflux and R2DBC, we saw that the application was more resilient and it held on for much longer. We saw exactly the same case with Webflux and Kotlin Coroutines. Using flows and using the suspend function, we were able to get the same shape in the graph for Webflux or Webflux with Kotlin Coroutines. Unfortunately, we were not able to test virtual threads, but these were just the examples with a database attached to the service. We were also able to test dummy endpoints, which only returned back to the client 10 products. For the traditional Spring MVC, we realized that the capacity wasn't that great when we had a strict limitation of the resources. We also saw that using Webflux alone without Kotlin Coroutines, we got a slightly better resilience, but the application service still went down. We saw that with this example, using Spring Webflux and Kotlin Coroutines, our web application never went down. And finally, we saw the same behavior with virtual threads. The overall conclusion here is that our services might be more resilient using Java virtual threads or using Kotlin Coroutines. They might be less resilient when using Spring MVC, and they might be a bit more resilient by comparison to Spring MVC when using just Spring Web Flux. But in terms of how fast the requests are being processed, there doesn't seem to be a clear conclusion here. They do differ, which points out to the main conclusion of this presentation, which is we are talking about resilience. And if we want to increase resilience in our web services, then we need to think seriously about if we want to choose between Webflux with coroutines, or simply using Java virtual threads, and how those choices will impact the libraries we use. To make this presentation possible, I had to do a lot of research on different materials online, and this is the list of everything that I've used to create this presentation. The slides are available right over here. You can find them on Scribd or in SlideShare. They will also be updated after this video. And you can find all of this source code and the documentation about Java virtual threads and Kotlin Coroutines. I had already done other projects to investigate these topics, and with them also articles that are now freely available on Medium. And those articles talk about different kinds of topics. For example, there's the Good Story project, where I compare CPU operations and the performance of these operations using Java virtual threads, using Kotlin Coroutines, and Kotlin Coroutines running with the virtual thread dispatcher. This was done last year, so I was still using a preview of Java virtual threads. That project has been updated, so that means that the results are now more realistic. I have this other project called the C Shell Archiver. This was the first project I ever made about reactive programming and about how can we potentially create a Spring Boot application using reactive principles, and this was using in combination with Project Reactor. Then I did also another project called Cozer Demos Root, which is a project that it investigates the first implementation that we had available for Spring Boot when it comes to reactive programming, and that was using Spring Web Flux and R2DBC. There are two versions there now, and they're all tagged, and the latest version is a Kotlin version with the implementation of WebFlux. So it doesn't use this Kotlin Coroutines, it just uses WebFlux, and there are instructions there to do these kind of tests, the ones that we like, the ones we did in this presentation, but instead of Locust, it is using JMeter. And finally, the last project, Kitten House Care Parent. It is a basic project on resilient services, but it's good if you want to know about how to work with services and you want a very, very simple example. Not to say that virtual thread coroutine cooperation project isn't a simple project, but this particular project was made for this presentation, and it focuses on performance and resilience. Or better said, it focuses on explaining that these topics are about resilience and not so much about performance. Finally, you can find these links about me. You can find my homepage, my LinkedIn profile. These are the two links for my channel. This is my Blue Sky profile link. This is my Mastodon profile link, GitHub, HackerNoon, DevTO, and Medium. I post regularly on HackerNoon, DevTO, and Medium. These articles are all for free. The articles on Medium didn't used to be free, but I made them all freely available this year. And so everything now is free to read, and the links to the GitHub repos are also there. But if you prefer, you can just go to my GitHub profile and have a look at all my work over there. And a big massive thank you now to everyone who came to the presentation, to the organizers, and for a great time in London, where we shared knowledge and we had great debates and we talked about different things. If you enjoyed this video, make sure to give it a like to this video. It helps the channel grow and it helps to raise awareness of the videos that I am posting here. Make sure to subscribe to the channel, that also helps the channel, and make sure to activate the notification bell so that you don't miss out on every new video that I post. I do post regularly in this channel, so if you are interested in these topics and other topics that I post over here, then you might be interested in having those notifications as soon as possible. If you'd like to say something special about this video, if you want to leave a comment, if you want to say anything, feel free to add your opinion in the comment section. I would love to hear your opinion, and hopefully I will see you in the next video. Have a good one.
As a short disclaimer, I'd like to mention that I'm not associated or affiliated with any of the brands eventually shown, displayed, or mentioned in this video.